right, welcome to Intro to Calc, day 1 of virtual learning. So on Friday before we left, we did these notes on the derivative and tangent lines. We talked about finding h of -1 with these points, and then we also talked about finding equations of two tangent lines if we weren't given a point on the graph. So now today we are going to learn about another alternative form of the derivative, and this way is a little bit easier than the way that we've been doing. And this one is, we have f prime of c is equal to the limit as x approaches c, way easier than before, of f of x minus f of c all over x minus c. Way easier than the formula that we were working with before. So we're going to do a first example. Use the alternative form of the derivative to find the derivative of f of x is equal to x squared plus 2x at c is equal to 1, if it exists. So first we're going to use that alternative form of the derivative, and we're going to, wherever there's a c, we're going to plug in 1. So, making sure you can see this. Okay. F prime of 1 is equal to the limit as x approaches 1. Our f of x function is the x squared plus 2x, so we're going to write that x squared plus 2x minus, when we find f of c, we're going to plug in the 1 in for x, so minus 1 squared plus 2 times 1 all over x minus 1. Now let's do a little bit of math to simplify this up. We have x squared plus 2x minus, this is 1 plus 2, so 3, all over x minus 1. Because the top is a quadratic, we can factor that out. Factors to x plus 3, x minus 1 over x minus 1, because what multiplies to a -3 and add up to 2. This now cancels, and we're left with x plus 3. But now we're really finding the limit as x approaches 1 of x plus 3. So when we do direct substitution, we get 1 plus 3, and our answer is 4. This last example is going to help us reach our third objective of this lesson, which is to understand the relationship between differentiability and continuity. So this alternative form, the reason why we do this alternative form is because it's useful in investigating the relationship between differentiability and continuity. So example, the function f of x is equal to the absolute value of x minus 2 is continuous at x is equal to 2, because what we know so far, the function x minus 2, the absolute value of it, looks like a v, and for the entire time we can trace the graph without picking our pencil up, which means that it's continuous at x is equal to 2. But now let's look to see what happens when we take the derivative from the left and the right side. So just like before, we're going to do the limit from the left hand side for the minus and the limit the right hand side plus. So we're going to do just that. We're doing x is equal to 2. So the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2. We're using this function for f of x instead of the previous example. So now let's do our substitution. We have the absolute value of x minus 2 minus the absolute value of 2 minus 2 all over x minus 0. This 2 minus 2 becomes 0. The absolute value of 0 is 0. So anything minus 0 is just going to stay the same. Absolute value of x minus 2 over x minus 2. So when we plug in numbers, since we're doing the left-hand side, numbers that are on the left-hand side of 2 would be the number 1.9999. So when I plug that in, absolute value of 1.999 minus 2 over 1.999 minus 2, you type that into the calculator, and you're going to get a -1. So we found that the limit as x approaches 2 from the left, using the alternative form of the derivative, to be -1. Now we're going to do the same concept, but since we tested it from the left, we're now going to test it from the right. The limit as x approaches 2 from the right of f of x minus f of 2 over x minus 2. So the absolute value of x minus 2 minus 2 minus 2 all over x minus 2. Again, 2 minus 2 is 0. The absolute value of 0 is 0. Anything minus 0 is going to stay the same. So we're left with the same thing as we had from above. This time, a number on the right-hand side of 2 would be 2.001. So when we plug 2.001 in for this, this time we get +1. So since 1 and -1 are not the same, we can say, even though f of x is continuous at x is equal to 2, it is not differentiable at x is equal to 2. What this means, the graph f of x does not have a tangent line at the point 2, 0. So that's all of the notes for today. I will post the picture of my notes completed up on Google Classroom for you as well. I'm going to alter this homework assignment because we've already done some of those problems prior last week while doing some of the review. But as always, reach out to me via Google Classroom or email, and I'm here to answer all of your questions.